Our first speaker for this session will be Mr. John Colley, a research fellow from University of Southampton. John Colley has 20 years of experience in the development of EDA tools for simulation, test generation, code coverage, and model checking. He is now involved in the ongoing development of verification and validation methods for high-consequence systems, both formal and simulation-based in the aerospace, defense, rail, and semiconductor sectors. So John Colley, over to you, sir.
Thanks very much. Okay, so what I'm going to talk about is how we can verify the interface between the human and the automation, the interaction between them and for safety critical intelligent systems. And the important thing is here, it's about the system. So we need to be able to do this verification if we want to develop some automation for a particular function. Okay, first of all, an acknowledgement. This work is being done under the ATI project sector, funded by Innovate UK, and the participants in sector are these companies, 10 companies. You can see those in your notes. Okay, so as I've said, safety is a property of the system, so the verification must be done within the context of the system. We want to do this as early as possible, so we're going to use modeling. We want to have a model of the system that we can verify the safety properties as early as possible. An intelligent system, we can model this as a set of interacting components. This is the natural way to do it. Component-oriented architecture is what we're going to end up with. And so early on in the process, we want to replicate that architecture. And for example, I'm going to use an aerospace example to talk this through. You can model the aircraft, you can model the automation of the aircraft, the flight guidance system, the autopilot. But what we also want to be able to do is model the human operators, the pilots, the ground staff. And if we're going to have to be able to verify this in a meaningful way, we're going to have to model the environment in which the aircraft is operating. Effectively, the window in which it's operating within the air. This can also be extended to the adversary and the bystander. So if we extended this into the security domain, you also be able to model somebody who might be attacking the system or an innocent bystander. So what we want to do is, using this model of the system, is use formal verification. In this case, we're going to use model checking, verify that the system-level safety constraints are not violated. Okay, so I'm going to go straight into a case study. And I guess some of you are familiar with this, and this is a speed protection incident, Colley Airport, 1994, and this is a reconstruction of what happened based on the accident report. So this aircraft, A310, is coming into land, 10:44:09, everything looks normal. And then a few seconds later, 10:44:14, suddenly the nose is up in the air and the aircraft is climbing very rapidly. Just over 30 seconds later, the aircraft stalls and falls out of the sky. The aircraft is only saved by the skill of the pilot. So what we want to be able to do is have a look at this. This is clearly an issue between the interaction between pilots and the automation, and how we can model this type of interaction. Okay, so this was the sequence of events from the accident investigation report. So the crew initiated the landing procedure, coming into land, and they have control over that. They set the aircraft mode to VSFPA. The flight path angle submode is the vertical speed mode. But as they're coming into land, the crew extended the flaps. Unfortunately, the airspeed was at too high a level to have the flaps extended, and so the autopilot invoked the speed protection capability to take off the speed that the airframe is in danger. The autopilot changed the mode from VSFPA to op climb. So the climb submode of the open mode. This prioritizes airspeed over vertical speed, and this caused the aircraft to climb with maximum thrust. The crew were confused. They didn't understand why all of a sudden the aircraft was climbing so rapidly. They thought it was a problem with the aircraft. That's what they said in the report. They disengaged the autopilot, but they did not disengage the auto throttle, which continued to command maximum thrust. And so the aircraft stalled. I guess this wasn't so well publicized because they say that nobody was hurt, but it could have been pretty bad. So as I've said, what we want to be able to do is, how can we prevent this kind of thing happening? Can we model the system early in the process and actually identify these kind of problems? And particularly, can we focus on avoiding the crew becoming confused? This notion of mode confusion is a serious problem with aviation. There are many, many similar cases to this where pilots become confused and there is an incident. So we're going to look at this at the system level, and what we want to be able to do is use some system theoretical foundation to this. So from the work done by Levison, and it's in this book, Engineering a Safer World 2011, and this book is online, we're going to use system theoretic accident modeling processes, STAMP. So it's based on system theory, and it's a change in emphasis from preventing failures to enforcing behavioral safety constraints. Safety is reformulated as a control problem rather than a reliability problem. So we're going to think about how can we control the system when we have human and we have automation. And STAMP is based on three main concepts, and this is the focus we're going to use when we do the investigation and analysis of these issues. Safety constraints, process models, and hierarchical control structure. Those are the three key things we're going to look at. So let's start off with the hierarchical control structure. This is probably the first thing you want to draw whenever you're investigating or looking at this type of system. So we have the pilots, we have two pilots left and right, and each pilot has a mental process model of what's happening with the aircraft and in the environment. The pilots send information to the automation, which is typically a state machine, and so there is a process model within the automation. The pilots can set the vertical mode, the altitude, flight path, angle. The pilots can also change the flap setting, so this is they can extend or retract the flaps directly to the aircraft. Also informing the automation, but this isn't done through the automation. The automation issues thrust and pitch commands to the aircraft. It monitors back the airspeed and altitude, and then in this closed loop, they alter the thrust and pitch. We also need to be able to deal with the environment. The environment which the aircraft is operating is also, the pilots themselves have a field, a seat of the pants field for what's happening within the environment. So that's what we want to model. And now so the issue with the speed protection problem was the feedback from the automation to the pilots did not include this change in mode. So the autopilot speed protection function can change the vertical mode, but it doesn't inform the pilot, and this is what caused the mode confusion. So the next thing after the control structure, we wanted to start looking at the process model. So this work is based on some foundational work done, Gilman, Fay, and Rushby, looking at applying these ideas to this particular case study. What I want to do is talk about more generally how you can apply this in general to autonomous systems. So the first thing they introduced is some work on how do you model the pilot. Now, fortunately, there's a lot of research being done into pilot behavior. So we have some cognitive theory outside of electronics and computer science, which has come to the conclusion that the pilot has a mental process model of the state of the aircraft and can be naturally represented as a state machine. So this is very useful for us because now if we're doing model checking, we can represent a model of the pilot as a state machine. The interesting thing they found about these state machines is that they do degrade. They degrade with time. Arcs tend to be collapsed into each other or disappear completely because they don't come across the corner cases very often. But very importantly, let's see that the pilot's behavior as a state machine changes and can disintegrate under stress. And that's something we would want to be able to model. So I'll go through what we presented in the paper, how they actually model this particular incident, and then talk more generally about how it can be applied in a wider way. So we have a model, a process model of the automation, and it can be very straightforward. We just have the notion is that the pilot is level, descending, or climbing. These are the instructions that the pilot issues to the automation: dial descend, dial level, dial descend, and the pilot's mental mode changes between these states. The automation, typically because of the instructions from the pilot, tracks what the pilot is telling it. So let's say starting off in FPA mode, if the pilot changes the mode, the state machine and the automation changes in line with that. The problem in this case was that there is an extra arc on the state machine here and here, where the automation itself can change the mode. So the mode reverts from FPA to off descent or off climb. So when we model this, we want to model those arcs. Now we want to move on and think about the safety constraints. How are we going to model the safety constraints, and how are we going to analyze what the safety constraints are? And so going back to the STAMP, we're going to use this process, System Theoretic Process Analysis, STPA, to actually analyze these safety constraints. So there's two main steps in STPA. You identify the potential unsafe control actions. Is there a scenario where the control action provides a hazard? Is there a scenario where the lack of a control action leads to a hazard? A potentially safe control action provided too early, too late, or in the wrong sequence, or continuous control actions too long, too short. So you do this quite systematically, and then once you've identified the unsafe control actions, then you determine how these could occur. So all we're concerned about in this particular scenario is the control action of the automation that does the assert mode reversion to climb. And so the first column is there a scenario we're not providing for a hazard? This was the original hazard analysis when the speed protection was developed. The hazard is H1, S speed exceeds maximum allowable speed with the flaps extended. What was not considered initially was, is there a scenario where providing this mode reversion can cause a hazard? And this is the hazard mode confusion if the pilot's mental model is the same. So something we have to consider explicitly as a hazard is a change, a control action which is issued, which confuses the pilot. So this analysis is done systematically. In this case, we're only concerned with the first two columns. And from this, we can derive natural language safety constraints. So this is what Harry Foster talked about just before the tea break. You always want to start off with your safety constraints with natural language, and these are derived directly from the STPA table. The first one is the one that they knew about. The airspeed should not exceed the maximum allowable speed. So what we add in this analysis is from the second column, the pilot's understanding of the current vertical mode was matched to actual mode. The last thing we need to do is we need to model the environment in which the aircraft is. And we want to use model checking, so we can't use simulation to do this, and it would be continuous simulation anyway. So it's an alternative formal approach to simulation-based environmental modeling. You take the differential equations of the environment, which are available, openly available, of that continuous domain, and we replace this with a set of assertions that establishes the relationship between the continuous variables. These safety constraints must hold whenever the relationships hold. Okay, so simply for this example, when the aircraft is in climb mode, the pitch angle must be positive. When the pitch angle is positive, the angle increases. So we can use constraints in our model, which simply says if the actual mode is climb, then the pitch must be greater than 0. And if the pitch is greater than 0, altitude take, that's in the next step. This is a synchronous system. The altitude will increase. So now we can put everything together and model the system. We've got to model the automation, model the pilot, model the aircraft and the environment. And now we just need a safety constraint. And so we can write some LTL, which says that if the mental mode of the pilot is in descend and the mode is FPA, then in the next, the automation mode must also be FPA. Typically, as Harry Foster said, writing LTL is not straightforward, and you're going to have a lot of properties. So what we do is we use, instead of a set of properties, we use a Gleason function. So a Gleason function is a formal monitor. We derive that from a formal system-level model, and this has access to the system-level sensor values in the aircraft state, and we can represent multiple safety constraints with a single property. So safety constraints can always be represented as a state machine. We can put them all together into a single state machine, and then we have a very simple way to check the violation. We can use this for simulation and formal, and we can also use this not only for verification, but at runtime. So We use USMV synchronous modeling method, so this is very similar language to Verilog and VHDL. We can have each of the modules of the pilots, the automation, the aircraft. We have our monitor, which is monitoring the system. And when we run the system, after 2 minutes on a laptop, we get a counterexample. And the counterexample actually reproduces the accident. It shows how the altitude changed when the pilot extended the flaps, and this change of mode and the way the aircraft climbed. So we're able to reproduce quite accurately what how that accident happened. So not just using this for verification, we introduced the policing function actually as part of the system. So it's actually there at runtime. And we can then move on to the next step, which is how we mitigate these unsafe control actions. So devising this hazard mitigation is very difficult. So their way of measuring. I have to go a little bit faster. And the natural way to do this is as a fault tree. So you have some mechanism, autonomous mechanism to avoid the failure. This is your automated system. If this fails, then this will fail. This is not a single point of failure, but it relies on the human to be able to intervene. And that means there must be a nice handover between the actual automated system and the pilot. To make this safer, you can introduce multiple primary handover and backup handover. To make it even safer, what we would suggest is you put the monitor, the policing function, actually into the system and use that to be the link between the automation and the pilot. But of course, then we have to reapply the process because it's safety critical. So in summary, formal modeling and analysis can be used to verify these interactions. We use STAMP and FTPA, and the policing function is developed formally from the requirements, ensures the safety constraints are not validated, mitigates against mode confusion, and enables this more effective handover from the failing autonomous function to the human one. Sorry, I've been a bit long, but any questions?
Well, before I go to my question, I think they were trying to indicate you're younger than you are early on. So you've been working for 20 years in this industry, like more like 30.
Probably
wouldn't it, if dawned on me listening to what you're saying there, that maybe a solution to this stuff, particularly the pilots, is if the automated system were having natural language interaction with the pilot, rather than necessarily adding more and more and more to the more formula and speak through. Because in the scenario you described, if the pilot had been told through the natural language interaction between the automated system and the pilot saying, oh, SB 2 times to engage flat, blah, 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 now going in, now I'm reverting to powered ascent mode, then the pilot would have known immediately through natural language interaction from the automated system exactly what's going on. And that is the cause of the problem in the first place.
So the idea is that the system level monitor, which you put into the system, has more knowledge than just the particular automation. Yeah. And it can talk to the pilot using, tell us which page of the instruction manual, or actually put the instruction manual on the screen. Yeah. So the fact is that the automation has got a wider view of the system and then gives the information to the pilot to avoid mode confusion. It could be natural language. It could be referring to the training manual.
Very interesting reference to Nancy Levison's work. Much appreciated. I was very impressed until the point you came up with a fault tree analysis. I know Ms. Levison in the preface of her book actually tells everybody that might have been working in reliability for the past 10 or 20 years, that the old days of failure mode detection analysis and fault tree analysis are reliability tools that have probably seen their day of safety analysis. Would like to comment?
I think what I thought is, how do you conceptually show that you don't have a single point of failure and that you can design the system so that there are multiple points of failure? And the AND gate. I'm just using the AND gate to say this and this and this. Just practically, there's probably a better way to do this. This is not a fault tree in the typical sense of the low-level design of the system and the actual signal. but a way of illustrating how you need to hand over and whether you can strengthen the safety by adding another component into the reliability analysis.
Thanks very much, sir.